This video is designed to give an overview of infrared spectroscopy used to identify functional groups in organic molecules. This, along with mass spec and NMR, can help us identify the molecule. Infrared radiation, when it's absorbed by molecules, makes the molecules wiggle. It doesn't break bonds. It doesn't jump electrons from one orbital to another. What it does is it makes the molecules wiggle. So let's take a look at that. These are going to be some examples of different ways that a CH2 group can move, and these types of motions have been given vocabulary names. So you could have them stretching symmetrically. You can have them stretching asymmetrically. You can have them bending like scissors. You can have them rocking, so these angles are changing, but the middle one wasn't. You could have them wagging, coming closer to us and further from us, closer to us and further from us. And you could have one coming closer, one coming further, so that's more of a twist. So these names have been given over here just so that we can talk about them. Different wavelengths, energies, infrared will make different kinds of vibrations occur, and that's really helpful. The units we're going to use, we're not going to use just straight out joules because you get ridiculously little numbers with exponents and stuff like that. We're going to use 1 over the wavelength, so it's a little awkward, the unit. It's how many waves are in a centimeter. Inverse centimeters, things per centimeter, and we're going to call that wave numbers. 50,000 wave numbers is about 1 times 10 to the minus 19th joules. This is an example of a spectrum. We'll take a look at some of the features here. Not a complete analysis. We'll do that in the next video. The x-axis is your energies. 4,000 is the max down to actually not all the way down to 0, down to about 500. And this is transmittance. So if all of the infrared light gets past the molecules, then it's got complete transmittance, and you wouldn't see any signal. If some of the light is being absorbed, then you get a downward peak. That means something is going on in this molecule. There are roughly 4 ranges in there. It's a little bit mushy, but it's a good way to think of it. This upper range here, from 2,500 and up. This one of the middle ranges from 25 to 2,000. From 2,000 down to 1,500 and here. There's nothing going there right now. And then below 1,500. And we're going to look at each one of those in some detail. Above 2,500, most of what's going on are something attached to a hydrogen, and then the hydrogen that's stretching. That can be either part of an asymmetric stretch or a symmetric stretch, but the hydrogen is moving, getting closer to and further from the heavy atom, the carbon, the nitrogen, or the oxygen. If the carbon has only single bonds, it's an sp3 carbon, methane, ethane, that sort of thing, then when the CHs are stretching, you're going to see peaks just to the low side of 3,000. So these peaks right here would be CH stretches, and it's very indicative that that's not from a carbon that's doubly or triply bonded. It's not from a carbon that's in a benzene ring. If it's got multiple bonds, then you're going to start seeing the CH stretches on this side of the 3,000. So this here is indicative of hydrogen stretching, but the carbon it's attached to is part of a multiple bond. The exact wave numbers, information can be gotten from a data table. I've posted one on the portal for you. You'll get hard copies as well. Over in here, in this range, we see triple bond stretches. And that's what's going on right here. It's a triple bond stretch. This is a CC triple bond stretch. And it's in this big empty region. You can usually spot that one. And so what we've got here is a C triple bond stretch. And over here, we've got an H stretching on a C that's part of a triple bond. So we have the H attached to the C attached to another C. That's 3 atoms in a row. It's very helpful in identifying the molecule. If it's a little bit lower than that, in this range, you would see peaks from double bond stretches. Either if it's a CC double bond, or the thing that's most obvious in this range ever is going to be if you see a CO double bond. There are also some peaks from benzenes that would show in this range. Down here, it's pretty unremarkable. There's lots of little peaks. Some of them are identifiable. Most of them are not. Most of them are these wags and twists. And any molecule with any number of carbons in it is going to have a lot of little peaks down here. This is called the fingerprint region. If you have the exact same compound, it will look exactly the same. If you don't have the exact same compound, it won't. So this is a quick run through of the regions, and this is what it's used for. To identify functional groups. You can tell if there are benzene rings or multiple bonds. You can tell certain groups. C double bond O is very easy. OH, I'll show you in the examples. And I'm going to make another video where we're going to have some example spectra and we'll go over some of the details.